So the main point of this is to get a little bit of practice drawing some Lewis dot structure and to be introduced to the different shapes that molecules can form. The reason we care about the shape is the shape shows if more electrons are going to be on one side of the molecule compared to the other, in which case you're going to have a negative side and a positive side, and your magnet, or your molecule will act like a magnet. It'll be what we call polar. So you can fill in this sheet that you guys have as we go. The first thing we're going to look at is an atom that just has one thing attached to it. So one atom, 0 lone pairs. It's going to be linear because, of course, you're just going to have this atom that has another atom attached to it. So 2 points connected is going to make a line. So linear. An example is HF. Fluorine has 7 valence electrons, hydrogen has 1, so I'm going to have 8 valence electrons to put on here. 2, 4, 6, 8. And it is polar because there's more electrons being drawn to the fluorine side. If I had 2 hydrogens or 2 fluorines, it'd be nonpolar because the electrons would be spread out evenly. Okay. And one thing we're also going to introduce as we go through this is hybridization. Hybridization looks at how many orbitals are being involved in the bonding. So the orbitals that we're considering are, for every energy shell, you're going to have 1 s orbital. There's 3 p orbitals, and there's up to 5 d orbitals that could be involved in bonding. Since this atom only has 1 electron pair involved in bonding, it's only s hybridized. There's just one thing, so the s goes first. And we'll talk about hybridization in class and what it means, but for the AP level, you just need to know how many things are repelling, and things are going to be groups of bonds. So a single bond is a thing, a double bond is a thing, a triple bond is a thing, or lone pairs. Those are all things that are repelling, and each thing is going to use 1 orbital for the hybridization. Next thing, the next molecule we have has 2 things on a central atom. So since there's 2 things, there's going to be 1 s orbital, 1 p orbital, and that's why we say it's sp hybridized. I'm going to give you an example where there's 2 atoms, 0 lone pairs. So you've got this central atom, and it's going to have 2 things attached to it. It's going to be linear, because the farthest away 2 things can be away from each other is going to be, and it's going to be 180 degrees. It makes a line. And the reason they're repelling, it's not the atoms. The atoms aren't repelling each other. It's these bonding electron pairs are getting as far away from each other as possible because they're negative. An example is silicon dioxide. So silicon has 4 valence electrons. Each oxygen is going to have 6. So I'm going to have 12 and 4. I'll have 16. So I'll go 1, 2, 3, 4 for the silicons, and then oxygen 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16. Okay, and you can see it's 180 degrees. If I have the same atoms attached to the central atom, it's a symmetrical molecule. So the negative side of this oxygen is bounced up by the negative side from the other oxygen. So overall, this molecule is not polar. And let's see. Next, we have 3 things being attached to the central atom. If you have 3 things, you're going to use 1 s orbital, 2 p orbitals, so it's sp3 or p2, sp2 hybridization. I'm going to look at 3 atoms, 0 lone pairs. So you're seeing you have this central atom with 3 things being attached: 1 atom, 2 atoms, 3 atoms. So it's planar, it's flat, and the farthest away these 3 things can get from each other, since these bonding pairs are negative, is going to be 360 divided by 3. So each of these is going to be 120 degrees, just getting away from each other. Then next, whoops, well, here. So 3 atoms, 120 degrees all the way around. It's trigonal planar. And an example of that is BCl3. So boron was one of our atoms that breaks the octet rule. It is satisfied with 6 valence electrons and can have up to 8. If I look in the periodic table, it's the 3rd column over, so boron has 3 valence electrons. I'll spread them out to make the bonds. It's bonding with chlorine, so I'll put a chlorine, chlorine, chlorine. Each chlorine has 7 valence electrons, so 2, 4, 6, 7, all the way around. Okay, so this boron is only surrounded by 6 valence electrons, and it's going to have the trigonal planar shape. The next guy, we have 4 things. So 4 things attached to a central atom. Since there's 4 things repelling each other, I'm going to use one s orbital, I'm going to use 3 p orbitals, so I call it sp3. Really, the level of AP is they just ask you, what's the hybridization of this molecule? And you can count things. Again, we'll talk about it in class, but that's all you have to do. I'm going to look at 4 atoms being attached. So 4 things will be attached to all the atoms. There will be 0 lone pairs. We call that shape tetrahedral. And what it looks like, you have one atom in the, like you have your central atom, another plane, another atom above it in the plane, another atom also in the same plane, one atom coming out at us, which is why I'm going to make that a wedge. Wow, it looks like it's just popping right out. And then a dashed line going back, and that's going to be an atom going away from us. So what that would look like is this guy. So I have these 3 atoms are in the plane, this one's coming out at us, this one's going away, and this is your tetrahedral. Okay. The bond angle around the tetrahedral, you can see it's not 90 degrees, so you're not going to go 360 divided by 4. This guy is 109.5. Let me just memorize that, or you can do some serious math. 109.5 degrees around every angle. So an example is CF4. I've got carbon, it has 4 valence electrons. Each fluorine has 7, so sometimes 4, 28. So I will have 32 electrons to put on here. So I'll put 1 electron, spreading it around because I'm going to make 4 bonds, and then every fluorine is going to bring 7 electrons with it. Okay, and then that's the tetrahedral. Tetrahedral is a big one to think about because tetrahedral, there's 4 things attached, and tetrahedral is the basic shape for tetrahedral, pyramidal, and bent. And the way you can do that is you can say, here's 4 things being attached, it's tetrahedral. Here's 4 things being attached, but 1 is a lone pair. We can't really see that lone pair, so it's pyramidal, it's a little pyramid, and that is the next shape. pH3. So there's still 4 things being attached. 3 are going to be atoms, 1's going to be a lone pair. So since there's 4 things being attached, I'm going to use 1 s orbital and 3 p orbitals. So this is also sp3 hybridized. And since it's sp3 hybridized, that explains why it also has that 109.5. Anything with the same hybridization is going to have the same bonding angle. So it's going to have that basic shape where there's these 4 things getting away from each other, but one of those things is going to be a lone pair, and the others are all going to be atoms. So I use a little dot to show the lone pair. And this guy, the lone pair repels a little bit more. So this was 109.5, but since that lone pair isn't localized as much, it's going to push these other lone pairs more. It's going to repel them more, moves around a little bit more. So this is going to be less than 109.5. Because it's squished. So maybe 107, somewhere around there. And pH3, you'll have your phosphorus. It has 5 valence electrons, so 1, 2, 3, 4, 5. I've got 3 hydrogens. Each one of those has 1 valence electron, so do that. All right. So this guy also has 4 things, so right away I know I'm going to use 1 s orbital, 3 p orbitals. I'm going to have 2 atoms and 2 lone pairs. I'm going to draw that same basic shape where I've got this central thing, a couple atoms attached to it. There's going to be 4 things attached, and this thing coming out at us is going to be a lone pair, and this thing going away from us is going to be a lone pair. So that would be like if I had my tetrahedral and I took off 2 of these guys, and then I'll just hold it the same way. I've got this, so I've got a lone pair coming at us, lone pair going away. Can't really see the lone pair, so it just looks like a bent molecule, which is the name of this. It is bent. I think I didn't write the name for this previous one. The previous one was pyramidal. And the one we have right now is bent, because it's a bent line, right? Okay, so an example, we have sulfur. Sulfur has 6 valence electrons, so I'll leave 2 for bonding. 1 for that hydrogen, 1 for that. So 1, 2, 3, 4, 5, 6 pair of the others. And each hydrogen brings 1 valence electron. Okay, so the bond angle here, now we have two lone pairs repelling, so it's going to be even smaller than this guy was. So we'll say again less than 109.5. So maybe this one's going to be about 105 if I had to pick a number. This was about 107. And I think that's all I have for molecules that are obeying. Yep, after that we start looking at 5 things. So now we're going to start going against the octet rule.